Hi students, today we are going to discuss about atomic size variations in 3D, 4D and 5D series elements from D block. Just try to know what are the 3D series elements. The 3D series elements are scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. Coming to 4D series elements, yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silver and cadmium. Coming to 5D series elements, these are lanthanum, hafnium, tantalum, tungsten, rhenium, osmium, iridium, platinum, alum and mercury. These are the elements belongs to these three series. The 3D series elements are nothing but first series in D block. The 4D series is the second series. The 5D series is the third series. Okay. The 3D series elements belongs to fourth period. So, all these elements will possess 4 shells. Means, we already know the shell number will always equal to the period number. Coming to 4D series, the 4D series elements belongs to 5th period. These will possess 5 shells. And 5D series elements belongs to 6th period. These will contain 6 shells. See here, the general trend in periodic table from top to bottom in groups. The atomic number will increase. If the atomic number increases, the shell number will automatically increase. The shell number will increase, the atomic size will also be increased. But that phenomenon is not working here. Why? Because let's see the reason now. See here, from 3D to 4D, the atomic size will increase along with the shell number. From 4D to 5D, the atomic size, there is no increment, considerable increase is not there. So, here it is virtually similar. What is the reason the similar atomic size of 5D to the 4D? The reason behind this one is the intervention of 4f orbital. Intervention of orbital. Intervention is nothing but involvement of 4f orbital you can use. See here, what is the intervention of 4f orbital? The intervention of 4f orbital is nothing but the 4f orbital going to be filled first. Going to be filled first. Then after 5D orbital will fill. This will results the decrement in atomic size or the decrease in in atomic size. The decrease of atomic size because of filling of 4f orbital first, then after 5d is known as, this process is known as lanthanoid contraction. See here, what is the reason responsible for the lanthanoid contraction? The reason responsible for lanthanoid contraction is the imperfect shielding effect. Imperfect shielding effect is, first of all you should need to know what is the shielding effect. The shielding effect is generated by the inner electrons to opposing the outer electrons towards the nucleus. That will known as shielding effect. So that is the main reason responsible for the lanthanoid contraction, means imperfect shielding of from one electron to another electron belongs to same set. Same set of orbitals. See here, I will explain you this one. The same set of orbitals are nothing but degenerate orbitals. What are those degenerate orbitals? Those degenerate orbitals are belongs to the subshells. Where these subshells present? The subshells are present in main shells. See here, if this is a nucleus, this is shell, second shell, third shell, fourth shell, fifth shell, and so on. See, the main shell contains, the first main shell contains only one subshell, that is the S subshell. The second main shell contains two subshells, S and P. The third one contains S, P, D. Fourth one contains S, P, D and F. Okay, these are the subshells, are nothing but orbitals. These orbitals will possess suborbitals. Those suborbitals are called as degenerate orbitals. For example, you can take d orbital. This is the d subshell. See, 5 degenerate orbitals are there. All these orbitals will possess equal energy. This is the d subshell. You can take f subshell. Here, F subshell will possess 7 degenerate orbitals. Okay, all these 7 will possess equal energy. So, what he said here, the imperfect shielding from one electron to another electron belongs to the same set of orbitals. Generally, orbitals are going to be filled first partially, nothing but half filled configuration. See here, 1, 2, 3, 4, 5. All orbitals are filled with each electron. In the same way, F also. See, after completion of partially filling, then they will need to pair up with another electron. At that time, the electron coming from outside to enter into that degenerate orbital, after entering it need to pair up with the inner electron. But what happens here, at that time the inner electron also has negative charge, the outer electron also negative charge. So the inner electron will opposes the outer electron towards the nuclear attractions. You just stay there only, don't come my side, because I am comfort with half filled configuration. I have so much of nuclear attractions. So why you are coming inside to me and why are you disturbing me? So just he think like that. So at that time the outer electron just try to enter inside, but the inner electron opposes the outer electron. So some repulsions will be generated between these two electrons, inner electron and outer electron. Those repulsions are nothing but inner electronic repulsions. Inner electronic repulsions. See here, in the same manner f orbital also contains. That means the same situation happens in f orbital also. So there are also some inner electronic repulsions. See, so that just try to compare between these two orbitals f and p, f and d. See, this is the 5d, just imagine this is the 4f. So which one has less repulsions, that one going to be filled first. So here the electronic repulsion between one d electron to another d electron is more when compared to the one f electron to the another f electron. So that f electron going to be filled, f orbital going to be filled first. So that 4f going to be filled first, then after only 5d. This is the reason responsible for lanthanide contraction. Coming to another one, is this lanthanide contraction applicable for all 5d series elements? No, it's not applicable for lanthanum. Why? Because lanthanum has 4f0 5d1 6s2. This is the outer electronic configuration for lanthanum. If there is f electrons, then only lanthanide contraction applicable. There is no f electrons for lanthanum, so that lanthanide contraction rule is not applicable for lanthanum. So from yttrium to lanthanum, the size will as usual increment is there, but from hafnium to mercury the size will decreases because all are having f electrons. So see here, zirconium to hafnium, the size minute increment is there. See, for zirconium that is 159 picometers, for hafnium that is 160 picometers only. So they both are having minute variation. In the same way, niobium and tantalum, see, molybdenum and tungsten, these three set of elements are always possess similar size. The remaining elements also possess similar size, but you have more number of bits from this one. So this is about lanthanide contraction. I hope you all understood about this topic. If you have any doubt, just try to let me know in the comment section. Thanks for watching.